class. As you may notice, in the first half of this class, I will be wearing a different shirt because the video was corrupted. However, let's begin. So today, we're going to be talking about the classification of Lie groups with simple Lie algebras. Big old underline there. Okay. Yes, indeed. So, last time we heard Andrew talk about simple groups and simple Lie algebras, and what it means for a group or an algebra to be simple. Yeah, just a quick recap on that. A simple group, big G, I will always refer to Lie groups as big G's, means that there are no non-trivial normal subgroups. Normal, let's denote that a normal subgroup is big N, normal subgroup of G, which recall we denoted with this little triangle. And yeah, just to recall, because there was a question about it the last time we talked about this, that what is a normal subgroup? Well, a normal subgroup, a normal subgroup is equal to sets. It's a set of elements in G such that G in G inverse is again in the set N. For all G in big G. Yes. So effectively, it's a group which is closed under conjugation. Right? And what does it mean to be a simple Lie algebra, small curly g? Well, this means that there is no non-trivial ideal subalgebra. We denote the subalgebra as little n and use the same symbol. Right? What does this mean? Well, this means that the ideal is a set such that for any element of the algebra, right, if I take the commutator of this element with any element in N, which I'll just write as the whole set in the ideal subalgebra, this will again be contained in the ideal. And so it's closed under this sort of commutator or Lie bracket, if you will.
So here little n is an element of little n?
Little n is actually the full set. Yeah, so more so I'm thinking if I were to take any element, in this, if I were to look at the set of all elements that I obtain, whenever I take every element in little n, and take the commutator with any element in the Lie algebra, I again get something that's in little n. The set of all these elements will necessarily be a subset. Could be the whole thing, but in general it will be a subset. Cool. Yes, indeed. Indeed. And so we last time we ended with the statement that, so this is kind of a recall.
Austin, another question.
Yes.
Do you mean n belonging to n in that, in the above line?
No, subset.
No, the one above that.
Oh,
when
the
you're
one
talking
above
about
that.
the groups.
Little n in G. No, yeah, so these are elements in G.
Oh, I see.
Right? Just such that it's a set of elements in G, right? But the idea is whenever I conjugate it, I get back one of these elements that's in N. Now, it's not necessary. This doesn't denote that, this is elements in G
Okay,
with
thank
this
you.
property. That's what I mean by this. Yes, great. Thank you.
Yes, indeed. Yeah. So I guess this was also kind of a recall.
But the statement that we sort of ended with last time was that just because we have a, if we have a simple Lie algebra, this does not necessarily imply that we're going to get a simple Lie group under the exponential math, right? Under exp. Right. And remember, we had a very simple example of this. If we considered the Lie algebra, little su2, right? Remember, this was generated by I sigma x and I sigma y. And whenever I write these square brackets, I mean these elements and commutators. Okay. Yeah. So this guy is simple. Because one can show, I mean, just by the sort of properties of Pauli operators, right? Taking commutators of these guys, we're never going to find an ideal. Right? However, but emphasis on that. The Lie group SU2 is not simple. Why was this? Well, because actually it turns out that there is a Z2 subgroup, right, of SU2, which contains the identity and minus the identity. And this was a subgroup, a normal subgroup actually, because everything commutes with the identity, right, by this normal subgroup property of big SU2. U. Yes. Great. Yes, indeed. So yeah, this is not always true. However, just as a point, one thing that we did end up getting at the end, there was a question that was asked, which we sort of discussed what the proof may be. Let's go ahead and do that now. Is that the converse of this statement actually is true, right? If I have, so maybe I'll write this as a theorem, because we will indeed prove it. Simple Lie group G does indeed mean that the Lie algebra that generates the group is indeed simple. How do we prove this? Well, proof. We're going to prove this by contraposition. So what does it mean to prove by contraposition? Well, we're going to prove the contraposition of this statement? Yeah, the contrapositive, that's what it's called. Yes, we're going to prove the contrapositive of this statement. So step one is we should suppose that suppose that G is not simple. Right? Then there exists an ideal subalgebra. Ideal subalgebra that we call N. Right? Which is an ideal subalgebra of G. Right? Okay. Sure. So now consider the group e to the little n. Right? What we want to show is we want to show, so the claim is that e to the little n is going to be a normal subgroup of e to the little g, i.e. big G. Right? How do we show this? Well, if we just consider elements of this group, e to the little n, maybe say e to the little n1, right? So I guess I should say let little n1 be an element of n, or sorry, little n. Right? Right? Right. Let's take this and let's conjugate it by some other element, little g, in the Lie algebra. So we take it, we conjugate it by e to the little g, e to the minus little g. Let's see what this is. Well, this is going to be, we can bring the exponentials on the outside into the exponent here, right? And then recall that last time Chris showed us this Baker-Campbell-Hausdorff lemma, which allows us to expand this as a series of nested commutators. Right? So we get e to the n1 plus the commutator of g with n1 plus a half the nested commutator of g with n1 plus higher terms. Okay. But recall, little n was an ideal of g. And by the definition that we have of ideal, this guy is contained in little n, and this guy is contained in little n, and so on and so forth. All other terms will be contained in little n, right? Because this property of invariance under taking commutators of the ideal subalgebra. And so we can say that this whole thing should be something that's contained in e to the little n. Right? And there we are. That's it. Thus, we know that e to the little n is a normal, e to the little n is a normal subgroup of e to the g. So big G is not simple. Great. And so then, by taking the contrapositive of the statement that we just proved, we know that if we go backwards, if this thing was simple, that would imply that G is a simple Lie algebra. Nice. Great. Great. Yes, indeed. So let's make a little remark here. Remark. Is that this is part of a general theme. This is part of a general theme we will see. We will not prove this in general. General theme. What is that general theme? It's that Lie subalgebras actually always generate subgroups. And it was something that Pablo pointed out. Subgroups of big G, the Lie group generated by the full Lie algebra. There's something that Pablo pointed out, that these subgroups don't necessarily have to be Lie subgroups. And then furthermore, Lie algebra ideals actually are always in one-to-one correspondence with normal subgroups. Which we sort of did just prove, right? Here, at least. Right there. If we have an ideal, we get a normal subgroup out of it. It generates a normal subgroup. Yeah, but we'll see this many times going down the line. Grab this chalk. Great. Can you see on this guy? All right. Good. Good, good, good. Yes. Okay. So now we ask, what does simple G get us? Right? I mean, we sort of just have this negative statement over here that simple Lie algebra doesn't imply simple G. But what does it imply? That's the question. And so yeah, we'll kind of write this fun little diagram over here. So suppose we start with a simple Lie algebra G. What does this get us? Well, in one case, I'll draw one implication over here. I'll call this implication A. The group that it generates is path connected. Actually, notice that this is more general than simple G. By virtue of the exponential map, we know that if we have a Lie algebra and we exponentiate it, simple or not, we're going to get something that's path connected, right? The exponential map gives you only local information about the Lie group generated by some Lie algebra about the identity. Only gives you information about the connected component. And yeah, just for good measure, let's just talk about that really quick. So I'll call this proof A. Right, so proving this statement is easy. At least it should be intuitive. Right. The idea is that for any x in G, for any element of the Lie algebra, e to the x is connected to the identity by the path the set of points e to the tx such that t runs from 0 to 1. Right? So the idea is that if I have any point out here in the group, if I make this whole bubble my group G, and add the identity over here, I can write a path connecting these two. And thus, if I have any other element, e to the x prime, I can draw a path from e to the x prime to the identity and then back to e to the x. Thus, any 2 points in the group are connected by a path. Thus, the group generated is path connected. Yeah, great. Great, great, great. What else do we get? Well, this one's actually the cool one. Is that any normal subgroup that I can find of the group generated by this simple Lie algebra must be discrete. Must be discrete. We'll call this statement B. And let's go ahead and prove statement B. How are we going to prove statement B? We are going to prove it by contradiction. Okay? Well, first thing that you always do in contradiction, let G be simple. And in the normal subgroup of E to the G, continuous. Right? Well, if E to the if N is a continuous normal subgroup, then there exists some subalgebra, which I will call, I don't want to call it little n, let's call it little a, which is a subalgebra of G, such that n is equal to e to the a.
Do you mean a triangle for A?
No, because I don't want it to be, I'm assuming that G is simple. So A is not going to be an ideal of G. It's
Okay.
just a subalgebra. Yeah, so in general, the triangle is indicative of an ideal subalgebra, but just the less than sign is indicative of a just a normal subalgebra. Right, because that's sort of the heart of this proof, right? Is that I'm actually going to show that this should be a triangle. And that's by contradiction, because I assume G is simple. Right? Yeah, much like with groups, right? I normally call this guy as a normal subgroup and this guy just an ordinary subgroup. Yeah. Yes. Okay, good. Yeah, there's a normal, so let e to the n1 be some, or I guess I should say e to the a1 be an element of e to the a. Right? Yes. Then we just do something very similar to what we've done before. For some G in the Lie algebra, if we conjugate this guy, we get exactly the same exponential of the exponents, which can be broken down into this series of nested commutators. Plus higher terms. Yes. And so the idea is to notice that if add G on A1 was again in A, this implies that A is actually an ideal of G, right? But that can't be true, because this means that that can't be true because we assumed that it was simple, right? And so the only thing that this could be is 0. So this guy must be 0. Yes. And so basically, what this implies that that n is not equal to e to the a for some a. Which this is some general result of Lie groups is that all discrete groups are not equal to some e to the a. So n is discrete.
So
Great.
was the Z2 and SU2 example that you had over there an example of this?
Exactly. Yeah. A normal set. So yes, because little SU2 is simple. The Lie group that it generates does indeed have a normal subgroup, but it turns out to be finite dimensional. And actually, as we'll see later in the lecture, is that it is this property, indeed, that allows us to, the property that in order to understand the structure of Lie groups generated by simple Lie algebras, we really only have to understand the structure of its normal subgroups, which corresponds to just figuring out what are all the discrete normal subgroups, right? Since all the normal subgroups are discrete, this is something that we can write them all down. And this will allow us to write down some big table when we classify all of these things. Yeah. Yes, indeed. Okay. And so then, so then the final statement then is to say, well, what happens if we combine these two? We use the fact that it's discrete plus the fact that it's path connected. Right? What do we get? Well, this is statement C. And statement C turns out to be the fact that that all of the normal subgroups of this Lie group is abelian and central. And just to give you some notation, because I think that this idea of central is a new concept to us. The center of a group G is a set of elements. V of G turns out to be a normal subgroup, which is essentially defined as the set of elements G in G such that GH equals HG for all H in G. Meaning it's the group of elements that commutes with everything in the group. Right? So we say that a normal subgroup of G is central if and only if N is a subgroup of the center. And in fact, it must be normal, right? Because of the abelian property, one could show this. Yeah, so that's what central means. The center of G is. Yes. So we will say that N has to be a subgroup of the center. Why is that true? Well, so this would be proof C, right? And this is more direct because N is discrete. And thus disconnected. So basically, in the picture that we have this Lie group, and we have elements of N1, N2, 2, and 3, so on and so forth. Right? They're all disconnected from one another. Right? So what we want to do is consider infinitesimal e to the g, which is an element of e to the curly g, which is equal to g. So consider an infinitesimal element of g. If we conjugate, so let n1 be an element of big N. If we conjugate n1 by one of these group elements, what we end up getting back is n1 plus the commutator of n1. Yes. n1 plus the commutator of n1 with g. Plus terms order g squared. We're not going to worry about these. Okay. The point is that this is an infinitesimal transformation, right? So we can sort of visualize this in the group as we go from n, and we do a slight transformation by this e to the little g. I guess you can't really see that. Right? But the issue is that if e to the if this is infinitesimal, there's no way this can take us from one component to another component, right? If there was something that's close enough, if there was an element that's close enough to n1 that it can be achieved by some small e to the g, I can always choose a smaller e to the g, such that it doesn't shift me far enough over in the group to get to the other element, right? So thus, this guy must be 0. The commutator must be 0. Right. So we have that e to the g n1 equals n1 e to the g. Should do a curly g like that. Right. But if this is true for infinitesimal transformations, and by the whole principle of what a Lie group is, it's something that we can get to other elements by compounding infinitesimal transformations, then this should be true for, if I compound infinitesimal transformations, if I build this up to a larger transformation. And thus, by compounding e to the g's, we see that for some more general element of the group, h in the full group, hn1 must be equal to n1h. So n1 is central. Must commute with everything. And furthermore, because of the fact that it commutes with everything in n, so I guess you could say that a corollary is that, I said n1 is central. Big N is central. So big N is abelian. So yeah, box over. Cool. And so there's one more thing that I should add over here that we are not going to prove. But yeah, I'll just write it down. Not proven. Here at least. The proof is a little technical and it gets a little hairy. We decided to omit it. But the idea is that if E to the little g, if the Lie group is compact, then N is finite. Meaning it consists of finitely many elements. It's not going to be something like the integers. Which again, we see here, right? Because SU2 is compact, as we know. And this is a discrete subgroup. Great. Okay. And so then, yes, so then the last little topic that we'll talk about before we jump backwards in time to the previous lecture is that, is that basically we now have a bit better of an understanding of the structure of these Lie groups, which are generated by simple Lie algebras, right? The idea is that to understand them, we really just need to understand, number one, the structure of the group, and number two, the structure of all of its normal subgroups, which turn out to be these finite abelian groups. Now here's the real power behind this, so this is kind of a remark or a statement that I will just kind of state with authority, is that there are finitely many G with the same little g. Right? Furthermore, there is a largest such G with the largest center. Yes. And so that's the idea, is that what we're going to do later is we're going to find this largest such G, which turns out to be something called a universal cover. And we're going to use it we're going to use it in its center, in all of the subgroups of the center, to produce smaller Lie groups with the same G, or the same little g, sorry, the same Lie algebra. And how does this work? So this is the big idea. Given Lie group G with normal subgroups G, which is a central subgroup because of the fact that we're considering G to be generated by a simple Lie algebra. Yeah, we can construct another Lie group, G prime, with the same Lie algebra, little g, via the sequence of maps and by maps I mean homomorphisms, right? Because we're talking about groups. We talked a bit about homomorphisms last time. The idea is we take this normal subgroup and we use an inclusion map to include it in G we project down to G by some canonical projection or some surjection, right? And the idea is that we want a certain property to hold, and that is that the image of iota should be equal to the kernel of pi. The image of iota should be equal to the kernel of pi. Which, as we notice, this is kind of means that this whole normal subgroup N is the kernel of the map pi. It's the thing that gets forgotten. And so as we notice, actually, whenever we have a homomorphism from one group to another, and we know the kernel of that homomorphism, we can actually construct an isomorphism, right? That was what was called the first isomorphism theorem. So this implies that actually G, oh my gosh, I'm so sorry. The prime should go over here, right? Because we had G with a normal subgroup, and we constructed the smaller group, right? So we project down into the smaller group. So forgive me for that mistake. Yes, so what we find is actually that G mod N is isomorphic to G prime. They have isomorphic structure other than the fact that this guy is sort of the same as G up to the fact that we modded out a few points. And this is something that one can use to convince themselves that we have exactly the same Lie algebra, right? Because we really only care about the structure of the group, about the identity to determine the Lie algebra. Right. Yeah, and I'll just kind of like give you a few terms here, just so that you can kind of take them with you and keep them in your back pocket. In general, I'll just kind of write it out to the side. This property, that image iota equals kernel pi, for any sequence of maps between any spaces here, is actually something that's very general that shows up a lot in mathematics. This is called a short exact sequence. So yeah, you can know what that means if someone says that to you. Furthermore, one other thing is that actually whenever these are all groups, so for groups with N being a normal subgroup of G, this is called an extension of G prime by N. And then yeah, furthermore, the one other thing is that for N being in the center, this is what's called a central extension. Cool. Now, yeah, this might seem like a bunch of just mathematical jargon. However, this will become an extremely useful tool to us. And actually, the next thing that we're going to see is going to be a very famous example of one of these central extensions that one can use to construct a smaller group from a bigger group. And this is actually the fact that SU2 double covers SO3. Where this double covering implies the fact that pi is a 2 to 1 map. Or homomorphism. Yeah, so in a moment I will teleport through time and you'll hear me talk about this.
Thank you, Austin.
Yes, thank you.